The following is a presentation of Southern Evangelical Seminary. The purpose of SES is to train and prepare men and women based on the inerrant and infallible Word of God to evangelize the world and defend the historic Christian faith with courtesy and respect. To find out more, visit ses.edu.
So does anybody know where the name Big Bang came from to start with? Who came up with that term originally? There we go. See, the problem is we have an actual scientist in here. Actually, it was Fred Hoyle who came up with the term. It was a term of derision initially, but we're going to talk a little bit about that. So what is the biggest bang, the biggest bang, that's what we're talking about. What was the biggest miracle described in the Bible? In the beginning, God created the heavens and the earth. I mean, how do you get bigger than that? And what better evidence for the veracity, for the correctness of the biblical worldview and the existence of God do you get than a miracle that's so well attested in ways that are just unimaginable 30 years ago or 40 years ago? We'll talk about that. And at the end, we'll have a little question and answer and discussion period. So if you have any objections or problems with any part of this or something you'd like to bring up or something you'd like to discuss, hopefully we'll have time for that too. And I'm going to be around past the 4:30 cutoff because it's dinner time anyway. If anybody wants to stay around and talk, we could do that for a little while. And Todd's going to hang around with me for a while because I'm driving him. So who's afraid of the Big Bang? That's my special effects. So here's what we're going to go through. What's a currently accepted version of the Big Bang? Because you know these things go through changes. I don't know, it was like 5 or 6 years ago, there was a headline, "The Big Bang's dead." And what they meant was one of the competing models had been eliminated, but they made it sound like the whole thing had been eliminated. What evidences do they have for this model? How can we use this information? And then the question and answer period. And just aside, anybody with scientific background, anybody work in sciences besides a geologist and a geologist also, and what do you? Okay. Anybody else? Yes. Nuclear engineer. Nuclear engineer. Okay. Maybe you could. Well, the parts I get stuck on, I'll just point to you. Okay. Aerospace engineer. Excellent. And
Chemistry.
oh, chemistry. There we go. We're going to be talking about a little bit of all of that in some sense. Hello. Welcome. Welcome. I'm sorry I may have started a second or two early, but there's a lot of stuff to cover when you're talking about.
Your salary, son.
You know, the biggest salary, by the way, welcome. I'm Don. Arnie, Don Deal. So this is the outline for this. What we're going to cover. What is the currently accepted version? And this is, and I'm not going to ask anybody to spit it out beforehand because there's different names for it and your name might be different. I'm going to give the longest possible name for it so you understand. We're going to talk about the different parts of that. The hot inflationary, lambda, cold dark matter, Big Bang theory. Did I get it all? What? That's a lot of words, isn't it? Is anybody in here already familiar with all of these parts? Or oh, good. That's perfect then. Oh, there we go. Yeah, well, different parts can be hot and cold. It's kind of like baked Alaskan. So we got some people who are familiar with these terms. That's good. And lambda is just a shorthand version of something that we'll get into when it's that part. So we're going to look at what evidences they have for each of those parts of the name. You know, what evidence do they have for hot, inflationary, lambda, cold dark matter, and Big Bang theory itself in general. So hot. Hot compared to what? Hot versus cold. Why is it the hot Big Bang version? Because somebody else, as we talked about a minute ago, had a different version. Anybody recognize this guy? His name's already been said. That's Fred Hoyle, Nobel Prize winning physicist from England who came up with a steady state theory back in the 40s because as we know, as we mentioned, Edwin Hubble had already discovered that the universe was expanding and he was trying to get rid of a beginning to the universe. So he came up with this theory that says that if you have so many molecules or atoms spontaneously generating within so many cubic billions of kilometers of space per year, then you could have an expansion without a beginning. That it's just an eternal, infinite universe. I can tell you the idea of an eternal universe obviously goes against a lot of basic ideas in science, but I mean, they could have known prior to all this that the universe had to have a beginning. If you've got an infinite universe with an infinite number of stars, if you look into the sky, what will you look at?
Another star.
Every line of sight will land on a star. It's called Olber's paradox. If you, it would be as bright as the sun in every direction, because over an infinite amount of time, all the interstellar gas, everything would have heated up, and everything would be glowing hot. And they also have the gravitational paradox, which says that under an Einsteinian system, that if everything was infinite and but finite in devotion size, but infinite in size but finite number of stars, they would have collapsed towards a central point. So something must be done. So Fred Hoyle came up with this steady state theory that says the universe continually creates new matter itself in a cold way. It doesn't require anything. And there's actually, within quantum mechanics, there's actually the virtual particles. Has anybody heard of that? Yeah. Do you know how many virtual particles they've actually observed? There we go. There's the correct answer. 0, which is why it's called virtual particles. And the theory is the more massive the particle is, the particle pairs are, the shorter their existence. And any particle of any measurable size would exist for too short of a time to even be measured. So that's why they call them virtual particles. And we'll get into that later on. If we have time, we're going to talk a little about Lawrence Krauss's book, A Universe from Nothing, because he says the whole universe is basically a virtual particle. So he said it should be cold. Well, that was a perfectly plausible theory. He had the math all worked out. He had a PhD in physics and a Nobel Prize. Pretty bright fella. It was possible. But there were two things his theory wouldn't be able to explain. And this is the two lines of evidence that proved him wrong. One's the cosmic microwave background, and number two is the relative abundance of hydrogen and helium in the universe. There's no reason it should be at the level it's at from a cold, eternal universe that continually expands, it creates itself. So there's the first one. 1965, I guess it was, Arno Penzias and Robert Wilson discovered the heat residue from the creation event. They found the heat left over from when the universe began. It's everywhere. If you had the old Rabbit Ears TV, if you went to a dead channel, part of that static would be part of the heat residue left over. And that cosmic microwave background, if you want to get biblical, is from the point when light separated. Is that kind of cool or what? But prior to that, the universe was too dense, and it was basically, it was too dense for light to be separate from anything else. This finding destroyed the hope of those two. I mean, this right here just destroyed them. You got heat. You got basically what they discovered is 2.7 degrees Kelvin, 2.7 degrees above absolute zero in every direction. Well, how do you get heat in dead space and deep space, wherever you look? Where do you get heat from? It's kind of like if somebody was cooking in the kitchen and left the oven open to cool off afterwards, and you walked in later and you felt the heat. You might think the house was abandoned when you walked in, it was empty, but there's heat in there, and that heat has to come from somewhere. And so his theory couldn't handle heat. And so this killed the steady state theory. So what was the second? How do they refine this even further? Well, this is from the Wilkinson Microwave Anisotropy Probe. They call it WMAP, and it's been refined even more than this. And this probe determined that the universe has a curvature of space less than half a degree, which is almost perfectly flat, but within a margin of error it could be perfectly flat. It determined that ordinary matter atoms called baryons, that's protons, neutrons type matter, that only consist about 5% of the mass energy of the universe. The density of the universe, about 5% of the mass energy comes from ordinary matter. And they found out that dark matter is about 24% of the universe. I mean, how interesting is that? What's dark matter? Well, we get to the dark part in a minute, don't we? And it determined that dark energy, which we're going to get to, makes up the other 71.4% of the universe, which causes the dark. Okay, we're going to get to the next part here in a second. Hot inflationary. So what else went wrong with Hoyle's theory? Well, the relative abundance of different types of molecules, atoms, carbon, hydrogen, helium. Well, the universe is about 70, at the origin of the universe, within the first minute, the universe was set to about 75% hydrogen, 25% helium, plus a few, with the little trace elements, lithium, and a few other things on top of that. Well, the only thing that would make that exact, if you do the mathematics, as the universe is expanding from an infinitely hot beginning, within a minute it will have made all the elements it's going to make from that energy. It will have cooled too much to make more elements. You can make heavier elements under high energy conditions, but the universe would have expanded and cooled too fast to form anything more, and they say when they do the modeling, it comes out to about 75% hydrogen, 25% helium. Now, that's not just something, that's a model, but it's a testable model in the sense that the energy levels required within nuclear accelerators, particle accelerators and such, you can reach these levels to test whether hydrogen fuses into helium at mega electron volt levels, and just in general, our accelerators now, like this one, the one in the Large Hadron Collider in CERN in Switzerland, this one reaches TeV levels, tera electron volts. That's 6 orders of magnitude more energy than you need to create helium from hydrogen. So that theory that the hydrogen helium was made at the instant of creation, that's testable at our energy levels. If you go further back into the first 1 to the, say, 10 to the minus 30th seconds, we can't reach those energy levels. That's all theoretical. But this level, the building of hydrogen helium, we can test that part of the theory. So those two things, the relative abundance of elements, the hydrogen helium, couldn't be explained under Hoyle's steady state theory, and the heat left over from the Big Bang, he couldn't expect that. So he gave up. He said, I'm wrong. He proved it. So what that did was get rid of an eternal possible universe. So what's the second part of this? It's called inflationary. Is anybody familiar with this part of the term? Yeah, this was in the news recently, this spring. And we're going to get to that in just a moment. This is, excuse me, I thought he popped up later. This is Alan Guth. He's the guy, one of the guys that came up with the original theory. He was the main guy. And the reason he came up with this inflationary theory, which I'm getting ready to explain, was because there were 3 problems that a standard Big Bang model, which that article saying the Big Bang model's dead, they're referring to standard Big Bang model. That didn't explain 3 things. One is the flat geometry of the universe, because it's so perfectly balanced between, we're going to get into it exactly balanced, but anyway, it couldn't explain the flat geometry. It couldn't explain the horizon problem, as they call it. That is, everywhere you look, the temperature is the same throughout space to within 1 part in more than 10,000. Now, the problem is, under a standard steady expansion rate, you can't transmit the information. You can't heat a cool area and heat area, hot area can't exchange heat. If you expand faster than that, you can have basically hot and cool areas that expand before they can cool and heat each other. So the horizon problem, that is the temperature being the same everywhere, wasn't really possible under a standard Big Bang model. So they needed something to explain that. And the final thing is, the standard Big Bang model, if you do the math, you should have some magnetic monopoles. Has anybody ever seen a magnetic monopole? Does anybody know what a magnetic monopole is? That would be a magnet that's either north or south. That's what the standard model said you should have. There are none. And so he came up with this idea, well, if there was a period of hypergrowth within the first milliseconds of the universe, that would smooth out things and help to take away all 3 of these problems. It would solve it. So the problem of the flatness of space, these are the 3 possible geometries. Think about it, you're on Euclidean geometry, regular flat space geometry. That's where you get triangle has 3 sides equal 180 degrees, parallel lines stay parallel forever. That's how we think of geometry. But there's also geometries of curved space, in which, if you think about it, if you drew a large triangle on the surface of the Earth, kind of like it's showing here, the 3 angles as viewed from above don't equal 180, do they? They're bigger than that. So there are possibilities. The chances from an uncontrolled Big Bang of having either of these geometries is greater than having this. This is knife edge stuff. This is extremely fine-tuned to get flat space, and yet they measured the space to be flat. So why do they believe in inflation? Well, why is the heat so uniform? They say that would explain it. I mean, if you're a young Earth creationist, there's not a problem here because you simply say God made it all, and that's why it's all the same temperature. You get what I'm saying? But if you follow the standard Big Bang cosmology, they can't explain why. So the inflation period, just a brief, less than 1 to 10 to the minus 20 seconds period of growth, of hypergrowth, faster than the speed of light type growth. And so that's the final thing that explains why there's no magnetic nanopoles. That all fits out. So what is that? Anybody know what that is? This was in the news back in the spring. Yes, sir.
In Antarctica, right?
Yes, sir. It is in Antarctica. It's the.
Telescope.
It is. It is. And what they were looking for was they were trying. This is the BICEP 2 station, which stands for Background Imaging of Cosmic Extragalactic Polarization. And I know everybody knew that to start with. That's why I didn't feel necessary to say it. So what were they looking for? If there was a period of the inflation that we're talking about that helps solve a lot of problems in the cosmology, then you should be able to see some evidence left over if you can get the fine enough studies done. And everybody who drives cars wears polarized glasses, I think. If you fly airplanes, you don't, right, Todd? But if you drive cars, you wear polarized glasses. It only lets light come in from one angle, right? And that way you don't get glare from everywhere. Well, they were looking for a very specific time, that cosmic microwave background, that heat residue, the infrared light. They were looking for a very specific type of polarization they call B mode. It's basically swirling polarization. And if that happened, then that would be, they call the smoking gun for the inflation period. Back in the spring, these guys said, we found it. And the guys who came up with the theory of inflation, I mean, they were in tears when the news came to them. We found the smoking gun. And that was very exciting. The main problem is that their data may have had some issues with it as other scientists looked at it. So all the parts of the Big Bang we're talking about today, this inflationary period, is the part that rests on the least solid foundation. And you can tell because I didn't show you any cool moving graphics of this part to explain, because if it's difficult to, if you have to conceive it and you can't actually see it, then it's probably on less, it's on hypothetical more than testable type foundations. But this one, they think they found it, but a group from Europe said, no, that's not it. The problem is, you're looking for a certain kind of polarization of light from the background radiation, polarized in a very specific pattern, but you're looking through our galaxy. You're looking through interstellar space. What about dust and things that can have cause problems with that? The team in Europe said the team from the U.S. that did this in Antarctica made some mistakes and didn't filter out enough of the intervening material to give them an accurate answer. So the inflation period is the most hypothetical part of this.
What are they planning to do? Are they planning to send up another?
The Europeans are already testing it, and they say, I think next year they hope to have the data from that.
Is it still an Earth-based?
I can't remember if the European. I think it's part of. Let me think of the name of it. They've already sent a satellite up. They're waiting to have enough data over a long period of time. The Planck probe. You know about the Planck?
How far out is it going?
I think it's beyond the orbit of the moon. I think it's that.
I know WMAP went up beyond the moon.
Right. So yeah, I'm pretty sure this is going to the same area, just with better equipment, more sensitive equipment. Lambda. This is the question most people had, and that's only because I picked one term out of 5 choices for this. Lambda is what Albert Einstein called this cosmological constant. This is the stretching property of the universe. You know, in Psalms it talks about God stretching out the heavens. This is the stretching property. Isn't it kind of interesting that the Bible keeps saying it first? And we're going to get some nice quotes at the end of this.
That's actually the coefficient of acceleration, right?
If you're talking about Hubble constant and all, yes, absolutely, yeah. And like I said, what we're going to do today is we're going to end with a short little theological reflection, but for the most part, we're just talking about the science today, because it's a lot of people think that scientists sit in laboratories and make stuff up. I just want you to see why they believe what they believe. You know what I mean? Because a lot of times I see in Christian writing, I see scientists as the bad guys. And they don't share our worldview, but I don't think of them as dishonest. They're trying, for the most part, they're doing the best they can with what they have, and they're excellent at what they do, obviously. I mean, if you don't believe in quantum mechanics, then throw away your cell phone. If you don't believe in Einstein's general theory of relativity, then throw away your GPS, because they're all dependent on those theories, and those theories have been tested, like the general theory of relativity, out to 19 decimal places. I mean, how much more tested? It's the most tested theory ever. I mean, you got to throw some of that out in order to throw some of this out. So lambda, the stretching property of the universe, that is, it's accelerating in its expansion. Did you guys know that? That's 16 years old now. The universe is growing, but now it's growing faster. Continually growing, and growing at a faster rate than it was previously. So the question is, why do they believe that? I mean, how far can you see with a telescope? Right? And you get your binoculars and look, and those stars, they're just dots in the sky. How do you know how far things are? So in order to determine that the universe is accelerating, you got to figure out first is, how far are distant stars? I mean, how can you know how far a star is? Parallax is the first one. That is exactly correct. Did you see my slide? Parallax. How far is that good for is a question. So you got to have increasing methods to increase your accuracy of distance. So beyond parallax, which we're going to explain in just a moment, you have to have what's known as a standard candle. You guys understand this concept? If I have a candle that burns at a certain brightness and hold it near your face, it looks really bright. If I move it a block away, it looks dimmer. But you can estimate how far away it is by how much light, how much dimmer it got. So if you have a standard, but how bright is a star? Depends on the star, right? So how can you tell how far away something is? Parallax works to a certain distance. So initially they use what's called Cepheid variables to measure distance as a standard candle, and I'll talk about that and the limitations of that. And then finally, in the late 1990s, a guy named Alex Filippenko and this group from the University of California started using type 1a supernovae, which we're going to actually have a really cool little video clip for that one. For standard. So parallax, how does parallax work? Well, your eyes, you'd measure distance with your eyes because there's a separation between them. What if your eyes were further apart? You can measure distance a little further. So if you use binoculars, you get more distance measuring. Well, from Earth, if you measured the angle to a star, remember the ancient Greeks measured the size of the Earth just by measuring the angle from a well of the sunlight, and they actually claimed pretty accurate measurements of the distance to the sun. You use parallax, you get two people in two different locations measuring the angle at the same time, and you just build yourself a simple triangle and do the angles, and you figure out, you get the base, then you can figure out the length of the sides. So you move to two different places, maybe one's in Italy and one's in the US, and you make your triangle that way. What about further out? Well, how about you measure the angle to the star during December and June when the Earth's at opposite ends of its time around the sun. There you go. You got a huge set of eyeballs now to measure difference. How good's that good for? About 65 light years away. So you can measure accurately about 6. So the nearer stars you can measure.
Ones that are moving with the sun.
Well, the ones that are, I'm not sure what you mean moving with the sun.
Well, I mean the sun is moving.
Yes.
Too.
Oh, absolutely. I mean, yeah, well, you're right. The galaxy is rotating. You got to, yeah.
Are moving, or shall I say, stationary relative to the sun.
Right.
That'll be accurate.
Absolutely. So that's good for about 65 light years. What about Cepheid variables? I mean, this one, obviously you have to compute, you have to negate the movement of the sun to the galaxy, the solar system to the galaxy. There's all sorts of things you have to take out to get an accurate measure. Absolutely. It's not a simple thing. It's not as though you just measure, and you got it. Then you got to subtract various things. But it's accurate. I mean, I don't think anybody disputes that the nearest star is a little over 40 light years away, that sort of thing. Yeah, that's pretty non-controversial. So what about Cepheid variable? That's my animation for a Cepheid variable. Does anybody know what a Cepheid variable is? Similar in concept, but different. Pulsars are, yeah. This is our standard candle, the first standard candle they discover. What they do is these stars have shells, gas, which they call doubly ionized helium. Basically, it's opaque. The helium blocks the sun, that star, from the light from getting out. So that helium shell will heat and expand. And as it expands, it reaches a certain level of coolness from getting away from its heat source, and it becomes clear after that, and it releases all the light heat, and then it kind of recollapses. And these things go from cycles anywhere from about 1 to 100 days. And when you do the math of how this works, how long it takes for that cycle tells you how big that star is. So if it's a one-day star, it's a small star, just pop, pop. If it's a giant star, it takes longer to get that shell out and reduce. So by measuring the length of the period between bright and dim of these Cepheid variables, you know the absolute brightness, how bright it is at its source. So then by measuring how bright it is from Earth, you can now tell how far it is. Does that make sense? This was discovered, I don't know, back in the 30s or so. And this is good for about 20 million light years away of measurement if you can find a galaxy that has these in it to measure it. Well, yes, sir.
20 million light years?
Yeah, the first one's good for about 65 light years. This is good, or 60 light years. This is good for about 20 million light years.
Not too far away.
Absolutely. So in order to determine if space is expanding slower or faster, that's too small of a distance to measure the expansion rate accurately. So what you need is the final thing, which is known as a type 1a supernova. And what it is I'll show you this. Oh, there it goes. On the right, you got a red giant. On the left, a white dwarf. The white dwarf is basically sucking the material off the red giant until it reaches a certain level called the Chandrasekhar limit, in which case it ignites. You get enough nuclear fuel near heat, and at a certain level, it'll ignite. It's a big nuclear bomb.
Continue to happen? Is that right?
This is a supernova, so this is a one-time deal.
So it wipes out that red giant?
Right. You get that one. It disrupts things so badly, but you get that one-time blast, and that is a pretty exact because you're starting with a white dwarf, and so you know how much hydrogen and helium it takes to pile up on top of that before it lights up, because those are pretty well understood. I'm sorry, do you have? Yes.
I was just asking what big light was, the supernova.
Yes, the
Big light, little light.
Yeah, here comes the supernova again. Yeah, this is the white dwarf. This is the red giant it's stealing its fuel from. And when it reaches a very well understood level, the force of gravity causes fusion to go off, causes it to explode. The size of this, when it explodes, is going to explode at a very precise level of light. It's a standard candle. And being a supernova, it's super bright, so you can see it from really far away. Yes, sir?
Do 1As turn into neutron stars or black holes?
Typically, you don't go from a white dwarf to anything else after that. Neutron stars and black holes require a certain size. Yeah, it's got to be about 4 times bigger than our sun at minimum, and that's already doesn't have enough mass. This is about the mass, maybe a little more than the mass of the Earth when it's compacted down to something smaller, like a 100-mile circle. So anyway, this is not nearly big enough to become a neutron star or a black hole. Those are formed under different conditions, but you're in the right line. So how good can you? How bright are these so that you can measure the light curve, the fall off from the distance? Well, they say that they believe these are accurate out to about 13 billion light years because they're so super bright you can see them that far away. And when you measure them, now you got a standard candle. That's what these guys in 1998 studied was they began to study the most distant galaxies, and seeing these things pop up in them, they began to study these and say, this is now evidence because we can see with a redshift, which we're going to get into later, exactly how fast they're moving and how far they are, and then you get an idea, well, the universe is now expanding faster than it ever did. Yes, ma'am?
Did you say billion or million?
Billion in this case. Yeah. This is good to about 13 billion light years. So we went from 65 million out to, what did I say before? I forgot what I said. 20 million. So you go from 60 to what did I say before? I said 65 light years, thank you, out to 20 million, out to 13 billion. So this was the real key to seeing, and I'll just keep showing that all day because it's so cool. That's a white dwarf with a red giant, and it's technically called a Type 1A supernova. There's different kinds of supernovas. You got all this, Todd? Thank you. So, cold dark matter. You guys heard of this? This is actually in the news fairly often. It's kind of cool. Cold dark matter, anybody heard of it? Yeah. Most people have heard a little bit about it. But what is it? Well, it's cold. We know that, right? And it's dark. We know that. And it's matter. So there's your answer. But neutrinos don't work because they're moving closer to relativistic speed, so they're not.
So hot dark matter.
Thank you. They're hot dark matter, exactly. So they're not a good possibility for cold dark matter. But we are going to. There's at least 10 to 15 different candidates for this, and it could be combinations of those. I'm just going to quickly mention 3 of them so you have an idea that they have some idea. But this is they have very good reasons to believe that there's cold dark matter. They have less good reasons to believe what that is. So we're going to talk about that now. So what is cold dark matter? Well, it's it's matter that doesn't interact with light. You can't see it. It's dark. Well, normal matter, if enough radiation from light and such hits on it, it begins to heat up and glow and such. This doesn't. So that's kind of weird stuff. It's not baryonic matter. It's not matter made of neutrons, protons, and electrons. That much we're sure. Well, they're not particles made of those things. Is there proof for this? Are they just making this up in order to confuse everybody? I think by now you know the answer is no. So this is I talked earlier about what the WMAP discovered as far as the makeup of the universe. It's about 75% dark energy, 21% dark matter, and about 4% normal matter. And those can be varied by a percent or two. So what are the possibilities? Axions. Anybody know what an axion is? Anybody ever seen an axion? No, you can't. It's dark, right? Axion's a hypothetical subatomic particle. What it does is, in quantum theory, they have they call the standard model where they have, 30 or so subatomic particles that do different things. Well, this one fills a gap within the model that they need filled in. So it's a theoretical particle, and if it exists, it could be, if there's lots and lots of these, then it would fit the model. Macho, these two I picked because I like the names. Macho is a massive compact halo object, which could be a black hole. If there's enough black holes, it could explain where the missing mass is coming from, because you can't see a black hole. They certainly don't glow, but they do have gravity. You see the effects of the gravity from the mass of it. Could be neutron stars, there's your word, because you can't really see neutron stars because they don't put out light. Could be very faint stars that we just don't see. But their light is so dim in the interstellar dust and everything else, we just can't see it. It's possible. Or it could be there's so many large planets and galaxies and such that we didn't even begin to calculate. In the case of planets, that seems pretty unlikely because you'd have to have a lot more planets and stars, and you'd have to have a really, really old universe to have time to make that much heavier elements to make the planets. But it's possible. And then the final category possibility are WIMPs, weakly interacting massive particles. That's another theoretical particle, and I think they picked that term just because it sounded cool. Yeah, it's a cool term, so you use it. Why not? So why do they believe cold dark matter's there? Has anybody ever seen the reasons why they talk about cold dark matter?
They can't find all the reasons. They can't find enough matter.
They can't find enough mass to explain what's going on. So we're going to show you exactly what we're talking about. In one of these pictures, I can almost guarantee very few people in this room have seen, even though it's widely available. Why believe in it? Well, to explain why we believe there's more mass in solar systems than you can see, first in galaxies than what we can see, I'm going to show you a model of our solar system in motion. It's not to scale, obviously, but you'll see, what I want you to look at is how fast the planets are moving relative to their distance from the sun. That is, are the ones near the sun slower or faster, or the ones further away slower or faster? So it explains the rotation of galaxies in ways that we can't explain because of the mass. And it also explains I got ahead of myself. Gravitational, also known as Einstein lenses. Anybody ever heard of an Einstein lens or a gravitational lens? Those are cool, aren't they? Have you seen the picture of it?
Seen some pictures.
Okay, we're going to show it for those who haven't. Just so that in case they think it's just a theory, that I can show you that actually they've seen what they pretty sure are. So what do you notice about, say, Mercury versus Neptune? Yeah, what you see is it's kind of like a curve. As you leave the sun, it gets faster and then slower as you get out. The curve should look like that. It should go up and then down. As you get further away from the sun, the speed should be less. So what do you do when you measure the speed of the stars within these galaxies that we can see, these spiral galaxies? We can see them, and we can measure the relative speed of the stars within it. What does that look like? Well, here's what it should be based on the model if there's so much mass mostly in the center, but here's what we actually measure. That is, the ones further out are going much faster around the center than they should be. It's almost as if those galaxies are solid. These out here are so gravitationally bound to the rest, it's almost as if they're solid disks spinning. The outer parts are spinning almost as fast as the inner part. And it doesn't make any sense unless there's a lot of mass in here that's holding them where they're at and making them go faster. It's kind of like if we had more planets within our solar system to hold them all, everything in line kind of thing. So when you measure what the calculations say, it's nowhere close. They're nowhere close to each other. The outer reaches are going much faster. It's almost like I said, it's almost as if they're solid material all the way out, holding them in place. Okay, this is theoretically what an Einstein or a gravitational lens, how it works. I don't know if everyone can see this, but basically you have a galaxy cluster in the middle of the picture. You have us here, and you have a distant galaxy far off, and the light waves are being bent. You guys know that under Einstein's general theory of relativity that mass will bend and make the light curve. They've demonstrated that many times over. So, have you ever seen an entire galaxy having its light bent? This is an actual photo from the Hubble Deep Field. If you look over here, these are the same galaxy when you measure the spectra of it. It's the same galaxy being shown multiple times. So this cluster is bending the light and causing the galaxy hidden behind it to be visible to us on these. So it has actually bent the light so that we can see them. The problem is, when you measure the mass of these galaxies, there's not enough to bend space that much. So you come back to dark matter. There's something in there that's causing space to bend and causing galaxies to move like a solid disk. And dark matter. Do they know what dark matter is composed of? We already talked about that. Unfortunately, no. They don't know. They got a lot of theories. And they're hoping that at CERN, the nuclear accelerator in France and Switzerland, they're hoping that one will shed light on it by getting to higher enough energy levels. Yes. Shed photons on it. Shed photons on dark matter. Yeah, exactly. Thank you. That wasn't meant to be a joke, but it came out better than I expected. Thank you. I'm gonna write that one in so I use it next time. So finally, the Big Bang Theory in general. That's the theory of cosmogony, meaning origin of the universe, that the universe began from nothing. This is not, they model it from something, but the theory starts from what they call a point of infinite density or a point of, they'll say, infinite smallness. Those are not terms that go together. There's no such thing as infinite smallness. Infinite and finite aren't different levels of the same thing, they're different things. When you say something's big, that's finite. If you say it's infinite, infinite doesn't mean really, really, really big. It means different category. It means that there's no end to it. There's no start to it. So when you say infinitely small, there's no such thing. What they're saying is nothing. And the scientists who study this, who do this, will tell you that basically what it means is it began from nothing. So that Calvin and Hobbes thing about a pen, that's where they can model it. But basically the theory starts from nothing. Yes, sir, do you have a question or just stretching your arm? Okay, it was the origin of space, time, matter, and energy. That's what the Big Bang Theory is. And there's the key word right there. The Big Bang Theory isn't the origin of matter exploding into pre-existing space. Kind of like a Newtonian idea of space that's out there as an inert playing field. Space did not exist prior to the Big Bang. Now wrap your mind around that for a minute.
as we understand.
Well, you'll have Lawrence Krauss talking about hyperspace, but
No, I'm just
yeah.
thinking, you know, if we believe God precedes the
Right,
universe.
right, but he's not
Transcends it.
right, but he's not finite.
Surely he can.
Here's how I think
I
yeah.
mean, basically, we're trying to we can't put God in a box.
Absolutely.
And so, at the same time, we cannot get outside of our own universe.
Right.
And so really is space, time, and matter within our understanding of what we are defined in.
If you well, that gets into some pretty deep philosophy.
Yes.
Immanuel Kant would call those pre-existing categories, that sort of thing, by which you organize information. But what the theory says is that space exploded into existence and took the matter and energy with it. Does that make sense? That it's not the beginning of matter, it's the beginning of everything. Prior to the Big Bang, there's not a before, there's just the Big Bang. If you think of, as Einstein did, as space-time, yeah, there is a beginning. And later on, I'll talk about where we know that there's got to be a beginning in an absolute scientific sense. Even if we talk multiverse, whatever, it's beyond that, and we'll get into that in a minute. So why believe in this Big Bang Theory? Well, that's a hydrogen lamp on the left, and if you look at, when you put it up a spectrometer, over here it's about 650 something nanometers, maybe 652 or something is a light. It puts out, different elements heated put out light at a very specific wavelength. Does that make sense? Hydrogen and helium and carbon, everything's heated, will put out light. That's how neon lights work in different colors. You got different gases in them. So you got that. Now this is the Orion Nebula. That's within our galaxy. And there it is. Same wavelength of hydrogen. So what do we think this is made of? Hydrogen. There's the wavelength of hydrogen. So what if you look further out outside our galaxy? This is a galaxy catalog number, but this galaxy, this little spiral galaxy here, the kind of dwarfed one, if you look at the hydrogen line, it's now over 660 nanometers. So in other words, it's shifted towards the red end. That's what they're talking about with redshift. Well, what causes light to shift like that? Movement. I mean, if you hear a train coming in the sound spectrum, if you hear a train coming at you and then it goes past you, you know, it goes from the higher frequency because it's moving towards you to lower frequency, it moves away. That light is shifted, indicating that galaxy is moving away from us. What if you look at a galaxy further away? What do you get? Well, there's the hydrogen line. Wait a minute, it's almost up to 700 now. So that one, which is further away, is moving faster away from us. So what it means is that, and you look in any direction, this is true. The galaxies closer to us are moving away from us. Basically, 99% of everything in the universe is moving away from us. There's a couple of clusters that are gravitationally bound to the Milky Way, but basically everything is moving away from us. And the further it is, the faster it's moving away from us. Well, what explains that? Well, what if you think of the Earth our solar system as being like a raisin within a loaf of raisin bread? As the bread expands, when it cooks, every piece of raisin moves further away from it. And the further the raisin start with, the faster it expands the space in between. So I'm going to show you a little graphic here. And what you're going to see is a bunch of galaxies, a red one, a green one, and a blue one. The red and green one are pretty close together. And the red one, which represents us, and the blue one are a little further apart. And then we're going to let it go through a certain amount of time and look at the difference in distance here. Okay, right now 1 million light years apart, 2 million light years. After a certain period of time, you look at it, and now this one is 2 million, that one's 4 million. The farther away it is, the faster it's moving away from us. So, the fastest parts of the universe we can see now and measure are starting to move away from us at close to the speed of light now, and some parts may be moving away from us faster than the speed of light. Or, then we can't, exactly. A scientist who's a materialist, atheist, whatever you want to call them, would say, we sure are fortunate to live in a time when we can see the whole universe. Because if we lived earlier in the history of the universe, everything would be too close together, too much light, heat, etc. We couldn't see everything. If we live later, most of it will move further away. We just happen to live at the right time. Very fortuitous. Okay, so why do they believe the universe? Yes, sir.
The fact
Right. Think about yourself on the surface of the earth. If I head north for 25,000 miles, where will I end up? Exactly. It's that kind of idea, that there is nothing outside, nothing physical outside of space. It's kind of like the origin, thinking of the whole universe beginning from nothing. That's mind-blowing. There's at least 100 billion galaxies with 100 billion stars on average each. That just blows your mind to think of that as being nothing to start with. So, what would you expect to see if the universe is the age they expect it they think it is? What you would expect to see is the further away you look, you should see younger galaxies the further away. That is, the light takes long enough to reach us. It should be early. Well, how can you tell a young galaxy from an old galaxy? A young galaxy is going to be more pure hydrogen helium, and the older galaxies have had time to make heavier elements. Within stars, you can fuse together hydrogen into helium, you can helium it into lithium, et cetera, up to about the time you reach iron. When you reach the iron stage, it kills the star because it requires more energy in than it lets out when it fuses. So iron kills stars. Anything above that on the periodic table either comes from supernova or come from our laboratories and we made them ourselves. So if we looked for the purity of stars, we should expect to see older stars or galaxies and stars here and younger ones farther away. That is, the farthest we can see, if we can see 13 billion light years away, then that's right at the Big Bang, right after the Big Bang. Then we should expect to see almost all hydrogen helium type stars here and heavier elements as we get closer. So this is what you should expect to see. As you look further out, the Gerber baby. Then as you look a little closer, you get to see Beaver Cleaver. Then you should see Gilligan. And then Greg Brady. Then Ted Danson. And then you should see the oldest stuff as you get right close to where we are now. That guy looks good. So when we look out in every direction, what do we actually see? What we see, as you look a little further, we see, that was the theory, here's the measurement. You see what I'm talking about here? It's what the theory predicted is what we're actually seeing in this case. So what are the physicists' reaction, the people who study this over time, what do they say about this data? Here is a guy named Robert Griffiths. He says, if we need an atheist for debate, I go to the philosophy department. The physics department isn't much use. And that used to be the case, but obviously Lawrence Krauss and Stephen Hawking claim to be atheists, but if you look at what they actually say about the science, they've moved way beyond experimental science into theoretical physics, and it's almost like the difference between Plato and Aristotle as far as, do you start from this heavenly idea and then try to work it to a knowledge of the earth, or do you start from what you see and work your way up? And those guys, the guys who are atheists and not astronomers, but physicists and such, and if they're into cosmology, they tend to be theoretical physicists. That is, they tend to deal with ideas and concepts. They can think of ways that maybe you don't need a God, etc. The guys who actually measure things and test things tend to be more into the theistic camp, and that's where this guy's coming from. And by theistic, I mean a personal God. Whether they believe in the God of the Bible may be different. This is Arno Penzias, one of the two guys that did the Bell Laboratory Big Year thing. He said, the best data we have concerning the Big Bang are exactly what I would have predicted had I nothing to go on but the 5 books of Moses, the Psalms, and the Bible as a whole. What else we got? Jeffrey Burbridge, he said, he was complaining, this is a few years ago, he complained recently that his colleagues in astronomy have all been too quick to join he called it the first church of Christ of the Big Bang. That is, that the origin of the universe was so powerful to him that there must be something that transcends the universe, a creator, that he was saying they're all running to that. So why do some Christians avoid it? Does anybody here avoid talking about the Big Bang? Is it because of lack of knowledge or because you don't like it? Does anybody here not like the Big Bang? Good, because I love it. I mean, obviously I'm here talking about it. Well, for some people who believe in a more recent creation, they believe the Bible. If you start with the Bible, they say, if I read the Bible, and there's people here at this conference who follow this, if they believe that the Bible teaches a more recent creation, then we must be in error in some way in our human reasoning is what they'll say. So some Christians don't like it because they think it teaches too long ago, and the current model has pretty much set the date of creation at about 13.72 billion years ago. And if you believe in a 6 to 10,000 year old Earth, that doesn't fit for you. So some Christians, excuse me? Well, yeah. But you know what's interesting is even for them, this is good stuff. Some misunderstand it to be like a bomb going off, like an undirected explosion. If you actually look at the fine-tuning parameters, it's ridiculously fine-tuned. It's almost like you got a buckets of paint against the wall, you throw a hand grenade in, and when you look up, the Mona Lisa's been painted on the wall. It's almost that idea. It's so finely tuned that random chance can't explain the physical constants of the universe. And some think it applies evidence for the evolution of life. They say if you give them a long time, you get time for evolution. But as anyone who studied, yeah, you're laughing because you know the difference. Anyone who studied evolution says if you look at it as a mathematical model, there's not enough time for it. I mean, so it doesn't, excuse me?
There's never enough time.
No matter what, I mean, I think next year I think about doing a talk on origin of life since I've already done DNA last year and Big Bang this year. I think next year I'm going to do origin of life. Anybody interested in that topic? Because the scientific stuff on it is so, if you study it, every book has weasel language. They'll say, it must have happened this way because there's no other way it could have happened. And literally they say the first proto-life, there's no evidence for it because all the first life ate it. So the lack of evidence is evidence for them. So how do we use this information? Well, it's a simple argument. Everything that begins to exist has a cause. This is pretty non-controversial except for specific cases. The universe began to exist, therefore the universe has a cause. If we just reason from that, what can we get to? Well, we could say the cause is extraspatial or non-spatial because space began and whatever caused it doesn't need space. Non-temporal because time began with the universe. Non-material because matter began with the universe. And I would argue personal because a physical cause would continue to act or not act at all, whereas a personal cause can choose, and the design implications, the design parameters of the universe indicate to me a personal creator. So, does it prove the God of the Bible? Not exactly. Does it get you 85% of the way there? I mean, if they can swallow the first verse of the Bible, how could raising someone from the dead be a problem when you can speak the entire universe into existence? I mean, they think the radius of the universe is like 42 billion light years. And if you get the power to speak that into existence, how could raising someone from the dead be a problem? Discussion. Anybody want to add anything or anything? I've run a little bit over, but not too bad. Yes, sir.
Well, since logically everything that ever came into being had to have a cause, then where would an atheist say the matter that was super compressed?
Well, we got two atheists who write on this regularly. Lawrence Krauss from Arizona State wrote a book called Universe from Nothing. And he said that the universe comes from, it's like a virtual particle that pops up out of hyperspace.
He redefined the word nothing, though.
Exactly. He says we misunderstand nothing. Physicists can't measure what we call nothing, but it has to be science. Therefore, we don't understand nothing, but nothing is something. Yes, ma'am. I'm sorry?
Have you written on this, or is there a resource about this?
Specifically, there's an excellent book called The Big Bang you can get. And downstairs, I'm a volunteer apologist with Reasons to Believe, Hugh Ross's book downstairs. He's got Journey Towards Creation's a DVD that covers a lot of this kind of stuff with much better graphics than I made up myself. And also he has a book, Creator in the Cosmos, that covers a lot of this kind of stuff. They're both excellent resources.
Why the universe is the way it is.
Why the Universe is the Way It Is also excellent too. And there's some people who are really good at geology who can be consulted on this matter too. Any more? Thank you. Oh yes, go ahead please.
Are there not a lot of Christian writers who also oppose the Big Bang
Yes.
theory? What would be their general
Because they think, number one, it's unguided, uncontrolled. Number two, they think it gives them time for evolution to happen. Number three, they think it doesn't sound, to them, you get creation day 1, 2, 3, 4. They can translate the Hebrew word yom in Genesis, which is translated day, has up to 6 different meanings to that word. They translate it to mean 24-hour period. And so therefore the creation event, you'd have to have a very long day 1 with a shorter day 2, etc. And so if you translate that as day, it doesn't work for them. It has to do with being true. They think being true to what the Bible says, whereas I say simply, yom has more than. We use the word, like the word yom can mean day or age, but we use the word day the same way in English. I say in my great grandfather's day they rode horses. Did my great grandfather live 24 hours? Pretty sure since I had my grandfather, he must have lived longer than that. So that would be why. Yes, sir.
Walt Kaiser was talking downstairs about
Absolutely.
genealogies and whether or not, and that a lot of times genealogies get compressed.
Yes.
And I think a lot of people who would hold to younger would hold to the literal 6 days of creation.
Right.
Or
Bishop Usher, basically, yeah.
by adding these genealogies.
Right. That'd be Bishop Usher's type thing, and they've been proven to be faulty. Yes, sir. Thank you for attending. Thank you. Thank you so much for coming by. Thank you. You're welcome. Thank you. Thank you for coming by. I'm sorry. Would you say that one more time, please? Right. Right. The question is, the question is the Bible referring to spiritual death or is it referring to physical death? And he's using the word death I mean physical death always, whereas the Bible talks about we were dead in sins prior to our salvation. And clearly I was not physically dead prior. I mean, I don't recall any resurrection events for myself. So obviously it has more than one possible meaning in that also. Yes, ma'am.
What was the second one? You didn't get two. I think the first one,
Uh,
about
that was Lawrence Krauss' second one, Stephen Hawking's book, The Grand Design, in which he says, if you have gravity, the universe can create itself from nothing. To which I say, I'm sorry, if you have what? Once again, that's what I'm talking. They're both theoretical physicists, and they both weasel around certain words. So you get people like that. You just simply ask, what do you mean by gravity? What do you mean by beginning? What do you mean create itself? Because obviously, logically, for anything to create itself, it has to exist before it existed, which doesn't make any sense at all. Yes, sir.
So would it be right to say that the theoretical physicists like Stephen Hawking are using deductive rather than inductive reasoning?
I'd say they're using a little of both, but they're not using. What they're doing is any deductive logic works as well as the premises. There's two different. Deductive logic has to be both sound, and the premises have to be true, and the form has to be valid, and then you get a sound argument. If your premises are false, then no matter how correctly you've reasoned after that, you end up with a false result. And so I'd say his premises contained falsehoods, and therefore his logic, though he was deductively valid, was not sound because he included a falsehood. Yes, sir.
Rabbit trail right here. What's
Sure.
your opinion on the quantum microwave engine? That they think might be a fluke like that?
I'm not familiar with enough of that to really discuss that part. But I would. The problem is they need a quantum theory of gravity in order to discuss beyond this. Yes, sir. What it shows is with that age of the galaxies and the expansion rate, etc., the universe needs to be about 13.7 billion years old, and that's clearly not within the 6,000 to 10,000. We're not talking about a little difference. We're talking big difference. So yeah, it would. So that's part of why they don't. Yeah, exactly. Thank you, everybody, for showing up today. I hope you got something out of this, and I hope. Thank you.